Okay, so in a nutshell, for the quiz tomorrow, we kind of did this before, but just to make sure that everybody's on the same page. So we want to go through kind of like chronologically how we got the idea of the atom to what we think it looks like up through the core model. The next thing we're going to talk about after this is the quantum mechanical model. That's the modern model, but that's not for the quiz tomorrow. That's where Bohr kind of was leading us there. So, who is credited with even coming up with the idea that atoms exist?
Democritus.
Democritus.
I can't believe I did that.
You know how his experiments are set up, what they're trying to find.
Sure.
He even gave us the basis of the name, right, for atoms, atomos. It was just an idea at this time because it was 400 BC, and we didn't really have a whole lot of technology there that could have given us any evidence of that. And it was an opposing idea. It wasn't even the most popular one. Who gave us the more popular one? Aristotle thought everything was continuous. Democritus thought eventually you would get down to a part that you couldn't divide, right? Keep breaking substances down, but you'd eventually reach this small part that you wouldn't be able to break down. And the way he described them, we could kind of make the analogy of Legos. And of course, Legos weren't around in 400 BC. In our thinking, for modern day analogy, because he thought atoms were different shapes and sizes, and that they just stuck together with one compound. That was his idea, his philosophy. Okay. And finally, when did we finally have some evidence that this existed? Who brought us the first evidence and the first theory? John Dalton. Around 1800, that happened. So, you know, a couple thousand years went by to but yeah, existed. Now there were 5 parts to his theory, and you can look. You should have those somewhere in your notes.
Is that going to be on the quiz?
Yeah, you should know what he basically just told us that everything is made up of small particles called atoms. Right? He thought that atoms of the same element were all identical in every way, right? Because we know today they're not because of isotopes, but we didn't even know subatomic particles existed then. So he said that atoms of the same element are identical in every way. Atoms of different elements are different. Okay. He knew that atoms combined in simple ratios to form compounds. He also told us that they rearrange themselves in a chemical reaction, that chemical bonds break and reform in different ways in a chemical reaction because overall nothing is created or destroyed. It just changes the way that they work. Now he did use 3 laws as basically part of his theory. He based his theory on these 3 laws. What is the law that tells us nothing can be destroyed or created? Right. So he utilized that, the law of conservation of mass. Because he stated in his theory that atoms cannot be destroyed, created, or subdivided. He said subdivided as well. Now we know today they can be subdivided, right, with subatomic particles. But if we do split an atom, it no longer has properties of the element anymore. So like we know fission exists today, right? We could split uranium and a whole lot of energy. Power. Once it's split though, it's no more uranium. he was right in that you can't break it down any further and still have that up. He also utilized the law of definite composition. Do you remember what that one is? Law of definite composition.
I don't know.
Just basically that when atoms come together to form a compound, they always come together in that same ratio. It doesn't matter. Like water is a good one because we're so familiar with water. What's the ratio that makes up water? Right, it's 2 hydrogens to 1 oxygen. It doesn't matter if you get water from a pond, the ocean, a glacier, from your spigot. It's always 2 hydrogens to 1 oxygen that make up the water molecules, right? So that was law of definite composition. And then he actually added this himself. He stated his theory and then added this a little bit later. Kind of like an offshoot of the law of definite composition. It expands it a little bit. Law of definite composition tells us that compounds are always made up of elements of the same ratio, right? Like water is 2 hydrogens to an oxygen. Then we also realized that we could make more than 1 compound with the same elements. But when we did that, they come together in different proportions, right? So like this is where we use that analogy of water and hydrogen peroxide, right? 2 completely different compounds. But he said they can come together in different ratios, but when they do, they come in different compounds. Okay?
So were these his laws or just like
this was definitely already in place. We already knew about the law of conservation of mass. The reason it played such a role is he didn't do the experiments himself. People were doing experiments in closed systems and realizing that, oh, we sometimes form these gases that we can't see. So things aren't just disappearing, they're actually present. Okay, and they did it in closed systems, getting the mass before and after an experiment, like burning something. So that was already in place. He did a lot of taking other people's experiments and putting it all together and saying, look, you know, atoms exist now from all these things that were happening. I do believe he came up with the law of proportion, so that's why he added it to his theory. But I'm not exactly sure if he actually did the experiments or if he utilized other people's experiments. It became part of his theory. He was kind of like taking the puzzle pieces and putting them together. All right, so does that make sense for John Dalton? And what was his model of the atom? Call his model of the atom.
Pudding or the billiard ball?
Billiard ball. So rather than thinking of them like Legos, where they're all just these different sizes and shapes and they just kind of stick together, he pretty much thought atoms were spherically shaped, right? Just different sizes, depending on what element they were. And that was the smallest thing. All right, so who gave us more information then after Dalton? J.J. Thomson, right. And what did J.J. Thomson discover? Electron, right. And it kind of makes sense knowing what we know now about atoms, right? Because electrons are on the outside part, so it's probably the first thing you're going to detect. Okay, so he discovered that electrons exist. What kind of charge do electrons have? Right. So it's really the negative charge that is affected. Really small negatively charged particles. What were his experiments? That was his model. came up with the plum pudding model, which makes more sense to us as the chocolate chip cookie dough model. But what experiments did he use to detect cathode ray tube? Yep.
Ooh, Georgia.
Cathode ray tubes are basically what old television sets and old computer monitors were. Just glass tubes at really low pressure. And he would run electricity through them. And what he found, in a nutshell, what he found was that if he would expose the electrical beam that was going through the cathode ray tube, if he would expose it to something negatively charged, it would deflect away from that. Or if he had the negative end of a magnet that he put towards it, it would deflect away from that. So the electrical beam that he was running through the cathode ray tube, he found that it always deflected away from a negative charge or magnetic pole, magnetism, negative magnetism, and attract towards positive charges or positive magnets. Now, like magnets have two ends, right? So when you put the negative end towards it, it would deflect away. When you put the positive end towards it, and he also knew that, remember I talked about the paddle wheels that he put in the cathode ray tubes, like the paddle wheel would always go from the negative to the positive end. So if you put like a free moving paddle wheel, it would always go from negative towards positive. So he knew that there was these negatively charged particles. He was also able to determine what about the electron, what mathematical information was he able to determine. Charge to mass ratio, right? So packed a lot of punch for its size, right? Packed a lot of punch for its size. Packed a really high charge for its mass. So you want to kind of think of see those short guys that always act real tough, right? Because they've got to make up for their size. So they're really tough for their size, high charge. But he knew what that ratio was. Like he knew a number for that. Okay, he knew what that number was, but he didn't know what the actual magnitude of charge was. He knew it was negative charge, but he didn't know how much. And he didn't know what the actual mass was. He just knew what the ratio between them was. Okay. And yes, he did have the plum pudding model. That's where he figured if there's something negatively charged in the atom, there has to be something positively charged to hold it together, right? So he viewed it as positive pudding with these negative raisins distributed throughout the pudding model. It makes more sense to us as chocolate chip cookie dough, like the dough is the positive stuff that the chocolate chips distributed throughout. So who came along and gave us more information about this part? Robert Millikan, right? So
Millikan. Roberto. I just remember the name in order.
So Robert Millikan didn't really change the model of the atom, right? He just gave us more information about the electron.
Yeah, sure.
What experiment did he use?
Was that the gold?
No.
The water, the mist.
Oil drop experiment.
I knew that.
I
mean, I knew that too, actually. And I kind of did.
And he used the oil drop experiment, and what did he determine from that oil drop experiment?
Oh, mass concentration.
He actually got the charge and then was able to plug the charge in, the magnitude of charge, and was able to plug it into JJ's ratio to determine the mass as well. Right?
I'm getting really. Quit laughing at the guy. I said stop that. Sorry.
Hey, people on recording. For those of you who are wondering.
All right. So in his oil drop experiment, he determined the magnitude of charge of the electron, and then could determine the mass using JJ's ratio, right? JJ Thomson's ratio.
Oh.
So he just gave us more information about the electron, didn't change the actual model of the atom. He actually worked with J.J. Thomson, so he was just kind of like moving their research further. And I did post like the links to the short video clips that we had watched of these guys in Canvas somewhere. I have links on there if you want to go back and watch them. They're very short and to the point, very dry, but very short. So basically his oil drop experiment, he just took basically a cylinder, had a plate in the middle cylinder with a little hole in it. Remember, he stole one of his wife's perfume bottles, and that's how he sprayed a fine mist of oil through there. Should probably need to buy a new one. All right, but he didn't want all that oil mist to fall down to the bottom at the same time. So that's why he put this plate in the middle of the hole, because he just wanted to focus on an oil drop at a time. These were charged plates, and he could control the voltage. And of course, these droplets were really tiny, so you'd look at them through a magnifying glass. Okay. But he also had to expose this atmosphere to X-rays. Why? What did the X-rays do?
You can see.
The inside.
Because these oil droplets by themselves are neutral, so they wouldn't really be affected by these charges.
Oh,
right?
doesn't it make them stay, like hover?
It gives them a charge by. This kind of should make more sense now that we talked about Bohr. But when you expose X-rays, it causes air particles to release electrons. So remember when we were talking about Bohr, how the atom gets excited, right? We put energy into the atom and the electrons jump to higher energy levels. X-rays are so much energy that they completely jump off the atom. They run out of energy levels and they completely are released from the atom altogether. So the X-rays cause air. Causes the air that's in here to release electrons, and then the oil droplets absorb. Okay. So then what he could do is cause these oil droplets, he put the voltage in there and cause it to hover. And he recorded the charge that it took for each oil droplet to hover above the plate. Each one was a different number of charge because they absorbed different numbers of electrons. But when he did enough of it, he could figure out, oh, they're all multiple of this charge. So that could determine the charge of one electron, which he then plugged into the ratio.
Wow.
So fairly simple experiment, right? But he got a lot. And he was very close to what we still believe the mass of the electron is today. Right? So that was Millikan. So now we know that these electrons exist. Who came along next and gave us more information about the atom then? And took us away from the plum pudding. Right. Is everybody good with this?
Yep. Anyone needs a picture, I will fix it.
All right, so then Ernest Rutherford.
Why?
What did he discover? Right.
Nucleus. That's what. I
You
said it.
just said that.
I said it first.
We need to know the years of these people.
No, I just gave years like for reference to see like it took so long to get
Yeah.
evidence, and then it's just like faster and faster we get more and more.
Has a stupid.
I'm working on my presentation on that.
Oh my god.
Okay, so basically from his experiments, he determined that there is a small, dense, positively charged nucleus, right? That's surrounded by a whole lot of space where the electrons are. Okay. A whole lot of space in terms relative to an atomic size. Okay. Not a lot of space to us, but the atomic level was. Right. So what experiment did he use?
Gold foil.
Oh, yes.
I don't know. He's lying.
Foil experiment. That's where he took a really thin piece of gold foil because you can roll gold out really, really thin. What did he aim at it?
Marble. Marble.
You rolled marbles to represent these alpha particles.
I love those. Those are the 4 and 2.
And alpha particles are positively charged, right?
Okay.
So they're actually made up of 2 protons, 2 neutrons, so they're positively charged.
Yeah.
And what happened to most of those alpha particles? Where did they go?
They deflected.
No, most of them actually just went right.
Oh.
Most of them just
And then-
passed right through the foil
Oh, that's
and
why I
went
thought
right
it
through.
was so small.
That's how we knew that there was space in the atom, lots of empty space, right? But
Y'all wouldn't let me teach this class. I would go that. Exactly.
a few deflected at different angles, right? A few of them deflected at different angles, even bounced almost straight back. The reason he could tell this is he surrounded the gold foil with fluorescent screen, right? So he could tell fluorescent screens, anything that's fluorescent, when it absorbs energy, it glows, it gets off light. So he could tell where these alpha particles were hitting because they have energy. And most of them were hitting directly behind the gold foil, but a few were deflected. He was surprised by that because he said that the force must be really high in that nucleus. There must be a lot of force. Kind of like taking a bullet, like shooting a bullet at a tissue and having it bounce off the tissue. That's kind of like the force he was describing. Okay. So that's how he determined that there was a really, 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 really small, densely positively charged nucleus that would be surrounded by a lot of space. So his new, he did change the model of the atom, but it didn't really have a name. Okay, he just had this nucleus, and then out here, these tiny electrons are zipping around. And this cloud, this electron cloud, is about 100,000 times bigger than it is. Okay. So we use the analogy of throwing like marbles at a dime on the 50-yard line of the football field, right?
Yeah.
How many would you actually get close to it? Probably not.
Oh,
Many.
yeah.
But every once in a while, you might get lucky. Those were the ones.
That's the most.
All right. Questions on that?
No.
Are we done with these?
Yes,
What?
Senora.
So now people wanted to know, well, how are these electrons staying out here? Like we have evidence that they're out there, but why aren't they just going back and sticking to the nucleus? And we're back to, then we're back to the plum pudding. So they must have some kind of energy associated with them, right? That they're out there. So who came along and gave us a little bit more information about that?
I'm thinking.
Oh, it's Niels.
No! Niels! Mr. Bohr.
That's where we ended, right, with Niels Bohr.
I was thinking, I was like, I don't remember anyone else besides Mr. Bohr.
Okay.
Who else gets bugs?
From Niels Bohr.
Yeah. Boom, boom, boom.
So he said that electrons are in these fixed orbits, right? Fixed orbits called energy levels.
We get the little mobile on that.
And he used spectroscopy, right? This keeps going E5, so on. I just stopped it. So what he did was said, what element did he focus on?
Ooh,
Hydrogen
Yeah.
was the simplest, right?
So
He used spectroscopy, okay, which is focusing on like the energy of light. So he would energize the atom basically by putting hydrogen gas in like a light bulb and turning electricity on. That would supply the energy. When the electron's as close to the nucleus as it can get, we call that the what state?
ground state.
Where you're just
But when we put energy in,
excited.
it cause the electron to jump. The atom would absorb the energy, cause the electron to jump.
The electrons.
And then when it comes back, it.
Right. So it absorbs the energy to go to higher energy levels. Then it emits the energy, right? It releases the energy in the form of different wavelengths, because sometimes it might jump all the way back. So, and then it would release a wavelength associated with that energy. And what he did was he associated that. He said, well, that energy must be the difference between E4 and E1, for example, or the difference in energy amounts between them.
Are we gonna have like these like math questions on this or something?
Like
You'll have those two equations that we went over. Yeah, that's the only math that's on there. But
Wait,
he said that
like,
the energy associated with this wavelength must be the energy difference between this energy level and this energy level. Okay, that's how he came up with the energy levels. That's how he defined them. But sometimes it wouldn't jump all the way back, like you said. Sometimes it might just jump back to here and give off.
the shorter jumps have a higher frequency.
Longer wavelengths. Shorter jumps have longer wavelengths, which is lower because they're inversely proportional. So the less energy, the longer the wavelengths. Okay, so this wavelength would be shorter because it's more energy than this one.
Yeah.
So that wavelength, that would be associated with E4 minus E3, for example, the way I have this drawn.
Yeah.
Okay.
Okay. See.
And so on. And it can jump back any number of ways. And then also keep in mind, we're only focusing on the visible spectrum, but there's also ultraviolet rays and infrared rays giving off that you can collect. You just can't see them. And that's how he defined all the different energy levels. And there were other people that defined them as well around the same time, like the Balmer series and Hess series, all that stuff. But that's basically how he defined the energy levels. And it worked really, 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 really nicely for hydrogen. So
Oh.
that's what's going to lead us into the quantum model next, after things. Focus, these are all considered the early models, and Bohr is kind of like known for the transition between early thinking and later thinking, because he went from classical physics of trying to define everything to
Question. What are we doing on Wednesday?
Oh, I wanted to talk to you about that. So Wednesday, I told the other class that if they want to bring in